Christoph Reinhardt, and with partially levitated membranes for high-frequency gravitational wave detection.
Okay. Yes. Can you hear me? Okay. Thank you very much, first of all, for the opportunity to give this presentation here. Thanks a lot for this. And yes, so in the following, I'll tell you about this idea to use basically an oscillating membrane for high-frequency gravitational wave detection. And here the membrane is installed inside an optical cavity, and where it interacts basically with the radiation pressure force inside the cavity. And its oscillation is partially controlled by this force. So of course, this setup looks very similar to the levitated sensor detector that we've heard about in the morning. But there is a crucial difference here. And this is that the membrane is structurally connected to the environment via a chip. And of course, this has certain impacts, which I'll talk about in the following. When I talk about the membrane, to give you an idea, basically, so shown here is this generic example of a square silicon nitride membrane, where you have some photos on the top left. And basically, so the membrane is a freestanding film, which is freely suspended from a silicon chip, which is made in a clean room, similar to semiconductor device fabrication. And so typical dimensions here are lateral extent of millimeters to a thickness of tens of nanometers to hundreds of nanometers. And silicon nitride is used typically for its very low intrinsic mechanical loss and its very low optical loss. Due to the extreme aspect ratio of these devices, the restoring force is not coming from the bending stiffness of the membrane, but it's really coming from the stress inside the membrane. So it's kind of a 2D version of a guitar string, basically. And then the resonance frequencies are given here by this expression, where we have the lateral extent of the membrane. We have this stress, basically the tensile, the tensile stress. And we have the mass density, and then we have these mode indices, which tell us kind of the lobes that we have in each spatial direction for given depending on the mode. And here for silicon nitride, we have this very high level of tensile stress, which is crucial of about a gigapascal. So what's shown here now is the conceptual setup of the detector, where we have the membrane installed inside the cavity, for example, by just attaching the chip to the input mirror. So we don't have to inject anything here. So in principle, we take the chip, could attach it ideally to this input mirror, and then it's installed. And the radiation pressure force here acts in a way that, as we've seen before, that the membrane is kind of attracted to the antinode of the field. So this concept is, of course, very similar to the levitated sensor detector. And what happens now as we displace the membrane around this equilibrium position, or as the membrane oscillates, is that there is this harmonic potential acting, and we get a restoring force. So by the optical forces itself, the membrane would oscillate. And related to this, we have this optical spring constant, which is given by the second derivative here of this potential. And so basically, it depends on the power, and the speed of light, and the wavelength of the light. And it also depends on the reflection and transmission coefficients of the membrane. And now we, of course, also have this mechanical restoring potential that we saw before. So the overall resonance frequency of the membrane is given by summing the spring constant, the mechanical one, the optical one, dividing by the effective mass. And here we can tune the resonance frequency with this optical power. And so basically here you adjust the power, and you change the slope of this potential, which changes the resonance frequency. So this has been demonstrated about 10 years ago by Jeff Kimball's group at Caltech, where they did this with a little glass pendulum, so chip scale glass pendulum, which they subjected here to this standing wave optical trap, And then they measured basically the oscillation with another probe beam and this quadrature photodiode. So to measure the displacement. And what they saw is that by applying kind of a couple of watts of power, you can tune the resonance frequency from few kilohertz up to almost 100 kilohertz. And then you start to be limited by mode mixing. So then you get to violin modes and so on of this pendulum. But anyway, you have a broad range of tuning here. So, okay, now we have an idea that we can kind of tune the resonance frequency. So how about the sensitivity? So similar to the levitated sensor detector, we consider the thermal noise to be a main limitation here. So the thermal noise coming from impacting gas particles which hit the membrane. On the one hand, and on the other hand, also the thermal noise from the intrinsic friction inside the membrane. So this is now an additional thing we have to consider. And what's shown here is kind of the setup inside a vacuum. So we need a vacuum to get rid of the gas damping. And also shown here is now the second field which we need for probing the motion of the membrane. And now, in order to get to relevant sensitivities, so we have to consider a few points. So basically what's shown here is similar to the levitated sensor detector, this thermal noise limited sensitivity. So we can see, okay, we benefit from having a long cavity, we benefit from having low temperature, high mass, high frequency, and of course a very high quality factor of this mechanical quality factor here. So in order to get to relevant sensitivities, then we consider here a pressure of 10 to the minus 11 millibar, which corresponds then to a quality factor of about 10 to the 13. So and now of course the point is that this is on the one hand due to the gas. On the other hand, this also means we need an intrinsic quality factor of the membrane, which is on this order here of about 10 to the 13. So I'll come back to this, which is of course an extremely high quality factor, but I'll get into the details about this. And then overall the goal would be with such a system to have a sensitivity similar to the levitated sensor detector. So we've heard about this a lot, so I won't go into the details again. But basically here I'm showing curves for a 1 meter long detector and a 100 meter long detector, because these are kind of the configurations that I'll come back to on the following slides. And okay, so how about the quality factor of membranes? So what's the current status? What are the perspectives? What you can see here is kind of the evolution of the quality factor over the past 15 years. And what you can see is kind of that it increased by 5 orders of magnitude. And this has been mainly enabled by just optimizing the geometry of the membrane. So it all started with strings and square membranes. And then during my PhD, I worked on this trampoline. And then people came up with other more sophisticated geometries, like this phononic crystal and so on and so on. And this enabled this improvement. And interestingly, pretty much all the points that you can see here have been realized with silicon nitride as a membrane material. So silicon nitride is an amorphous material, and it has long been known that in principle by using a crystalline material, which can be made much purer with lower defect densities and lower intrinsic friction, you could get to higher quality factors, but only recently it has been possible to show this actually and to make a crystalline silicon membrane. And this is here the current record. So this was done in Tobias Kippenberg's group at École Polytechnique. So okay, so now we have 10 to the 10 to the 10 in terms of quality factors. So how can we get to 10 to the 12, 10 to the 13? And basically the strategy that we are pursuing here is to use this phononic crystal membrane. And this membrane is characterized by this honeycomb lattice of holes, which is punched into the membrane. And then we have, which acts as a phononic crystal. So, and then we have this central defect here. And basically what you can see here is this localized mode in the defect And it's localized because the phononic crystal is designed in a way that it suppresses the propagation of these elastic waves due to destructive interference. And this is nice because it decouples the oscillation from the parameter range where we typically have the highest losses. And okay, now the scaling of such a membrane, as you can see here, so we have this geometry factor, then we have the lateral extent of the membrane, we have the thickness of the membrane, and then we have this tensile stress that I talked about at the beginning, and then of course also the intrinsic friction, which is this imaginary part of the Young's modulus. So the idea would be to scale them up in terms of size. Currently, these devices, they have a lateral extent of a few millimeters, and this results in a quality factor of 1 billion resonance frequency of on the order of a megahertz for silicon nitride membranes. So the idea is to make them 10 times bigger. You get centimeter devices, which then, according to the scaling, have a quality factor of 10 to the 11. And then instead of using silicon nitride, we would use silicon, which could give you an additional factor of 10. So then you have on paper Q10 to the 12. And by optimizing the geometry and so on, we might get to 10 to the 30. Yes, so this is one part. And then, of course, this tunability is a big question here. Okay, so you have this phononic crystal device, which, of course, is more complicated than a pendulum. So how about the tunability? And what has been shown in the literature is that you can make phononic crystal membranes where you have a tunability of this defect mode of about a factor of 2. And then based on this, we would expect that we could cover the substantial range of tens of kilohertz to hundreds of kilohertz with 5 such membranes, basically. Okay, once we have the membrane, then we could think about how to realize a prototype detector. And this is kind of sketched here, which again looks very similar to the levitated sensor detector, where we have this Michelson configuration of 2 cavities for detecting some common noise sources and so on. And then in each arm, we have a 1 meter long cavity with a centimeter scale membrane. Everything cooled down to 10 Kelvin, for example, which the membrane likes to have a high Q. Yes, so this would be kind of the idea here. And then, so okay, how about the current status? So are these systems realized at all and so on? And luckily they are. So this is kind of a branch of research by itself, cavity optomechanics. Some of you here know it, of course. Very well. So just to give you an idea, I mean, currently these systems, for example, they look like this, where you have millimeter long cavities and millimeter lateral extent membranes. So the scale, of course, here is different compared to what we are looking for. So we would like to scale it up to centimeter membranes and meter scale cavities, and in the end, even 100 meter long cavities. But yeah, you can make them longer, so this is not the question. So during my PhD, I worked on something where we had centimeter long cavities, and yeah. Okay, and yeah, with this, I would like to summarize by giving you kind of a current status and possible next steps. So we submitted a grant application in order to realize these large membranes. This we did together with Albert Schlieser's group from Copenhagen and Benno Wilke's group. So Albert Schlieser's group actually invented these phononic crystal membranes. Yeah, then I'm also working towards a grant application to realize such a prototype detector. And if one would like to dream about a future realization of a full-scale detector, then of course the ALPS 2 experiment at DESY comes to mind, which comprises 200 meter long cavities. And so you can see here kind of this infrastructure where there's also the cryo platform at DESY, which provides the cryogenic environment for realizing such an experiment. And related to this, of course, all the expertise is available at DESY. So we have the optics experts, controls, vacuum cryogenics, you name it. And so basically Axel will give a talk about this tomorrow at 3:30 and tell you about all these details about ALPS 2 and the infrastructure at DESY. And in the end, I would like to close with a little advertisement. So there's also some nice synergies that can be exploited with regard to using these membranes. So I mentioned that basically the thermal noise is a limiting noise source due to this hitting gas particles on the membrane. But this effect can be used actually to make a very nice pressure sensor. So the membranes are great for sensing pressure, and this is what we are working on currently in a second line of work, where recently we showed that using a membrane enables to measure pressure over 10 decades, which to the best of our knowledge is kind of the widest range that has been realized with a single sensor. And this is work that we are doing together with Roman Schnabel's group from the University of Hamburg. And with this, I would like to thank you very much for your attention.
Okay, thank you. Is there any questions? Yes?
Thank you, Christoph, for that very nice talk. I had two questions. One is, in the beginning, you said that you were going to use the optical spring effect to make the detector out of this, and then I saw the frequency of the membranes was the mechanical frequency that you're targeting is 1 megahertz. So can you clarify the two different frequencies?
Yeah, of course. So this is something I didn't mention explicitly, but so you have the scaling here with 1 over L. So and then what I showed you is so remember the scaling, which I should have put back here, of course. So you have here 3 millimeters, and this corresponds to a megahertz. So if we go to 3 centimeters, then we are already at 100 kilohertz with this 1 over.
And so, but that would still be the mechanical resonance frequency, and then the optical spring, you still need the optical spring to be higher. So I think we have to be a little bit careful to build gravitational wave detector because of the discussion from last session. Like the question that Valerie asked, what is the actual coupling of the gravitational wave? The gravitational wave coupling to mechanical mode will be different from the coupling to the laser's antinode position. So if you want to sense the antinode of the laser, then you want to be in the regime where the optical spring frequency is much higher, is much stiffer. So if your mechanical frequency is 300 kilohertz, then you're sort of not in a very clean regime. Does that make sense?
Yeah, no, I mean, this is true, of course, but there are many ways how you can deal with it. I mean, you can change the frequency with the mode shape, you can change it with the size, you can change it with the stress level in the nitride. So there are definitely a lot of parameters you can tune in order to get to this regime where you're clearly dominated then by the optical spring.
Yeah. And what is the laser waste that you guys are thinking of building?
Yeah, this is of course an important question. So let's say if you so the laser waste will depend on the size of this defect. So we want to have the laser beam to be well contained within this defect so that we don't get all the scattering and so on. So one approach that people typically take, for example, in this paper here, is to have the beam diameter to be the half of the radius of this defect. So about this size, you have very high scattering limited finesse.
What is the rough number?
For the scattering limited finesse?
For the base?
Okay, so basically, let's say we scale this up by a factor of 10, then this defect would be about 3 millimeters. So then half of this would be 1.5 millimeters. So then you take a beam on the order of 1 millimeter waste. Yeah.
Yep.
I'm sure you said it, but how do you actually read out the deformations?
Yes, so this is the second beam. So there's one beam. This is exactly the same as to first order. My naive understanding is that this would be the same as for the levitated sensor detector, where you will have one trapping beam and then another beam for reading it out. So where you have this difference of the quadratic coupling and the linear coupling. So in order to sense the motion, you want to be linearly coupled. This gives you a better response. So this is basically the second field which is shown here.
I have a question. So basically, you've got a really soft spring. So the way I see it's different to the levitated system is that you're just changing the spring constant of the soft spring. Is that right, or is it?
Well, we have an additional spring, yes. So we have two springs. We have the optical spring and we have the mechanical spring.
But if I have just a parametric transducer on an acoustic oscillator, I can change the spring constant just through the transductance. But this is, but you've got a separate readout. But you can, that is a parametric effect. So is this a parametric effect, or is it the same thing as an optical spring?
I mean, so here, my understanding is really to have this kind of system.
Yes, so it just adds to the spring constant. That's
exactly.
Right,
yeah. So you have two spring constants, so one
right.
coming from the mechanical system, one from the optical.
Okay, any other questions? Yes, one up there. Yeah, we're taking up our question and answer time here. That's all right.
Hi, thanks for the great talk. Maybe you mentioned this already, but do you have plans to cool the membrane optomechanically? And
yeah, it should be. It should be, as we heard in the morning, to get to a reasonable bandwidth, you need to cool it because right now you have a Q of 10 to the 12, 10 to the 13, so your line width is extremely narrow. So to get to a reasonable bandwidth, you need to cool it to broaden the line. And at the same, so you reduce the Q factor at the same time as the temperature. So you keep the force sensitivity, but you increase the bandwidth.
I see. And I guess this cooling doesn't cool away your signal necessarily, or how should I think about this?
The cooling should not cool away the signal. So I would have a different. I have a different perspective. You don't increase the bandwidth by cooling. You increase the line width of the acoustic oscillator, but that's not the bandwidth of your detector. So yeah, you increase the line width. Yes. Sorry. I mean, you make the line width bigger, but that's not the bandwidth of your detector. Q on T remains constant, so you gain because the thing doesn't ring. If you got 10 to the 13, you'll hit it and it'll just ring all the time. You don't want that. You need to cool it, and you to a lower temperature, and the Q goes down. That's easier to manage experimentally, but it doesn't change your sensitivity one bit. Doesn't change the bandwidth one bit. You still get the same level of noise, and it depends on your readout noise what your bandwidth is. Mm-hmm.
I think it does change your bandwidth in the sense of, like, if you just draw like an inverted resonance and then you draw a flat line of shot noise, which is your readout noise. So now if I change the narrowness of the inverted resonance, if I'm making it wider, that opens up a wider region where your shot noise is... No,
because the gravitational wave signal and the thermal noise see the same transfer function.
I agree, but I'm saying if I convert everything to the gravitational wave transfer function, then what is what is the shape? That's why I'm drawing the inverted thermal noise.
Yeah, so that's due to the readout noise.
Yeah.
Yeah.
So the readout, the place, the bandwidth in which you're sensitive to the readout noise becomes broader. So that's why your detector bandwidth becomes higher. That
depends on how much readout noise you've got through the transfer function.
Absolutely, yeah.
Any other questions?
So you mentioned obtaining Q factors, greater than 10 to the 12 with bigger membranes.
Yeah.
And you mentioned using silicon instead of silicon nitride.
Yes.
But can you get the same level of stress, internal stress in silicon, in crystalline silicon that you can get in silicon?
Yeah, this was exactly one big point, I guess, which also led to the delay of making the silicon versus the silicon nitride membranes. But basically, these here, they have a tensile stress of 1.4 gigapascals, so which you can get. So it comes from semiconductor fabrication. So Soitec makes these because you benefit in terms of high electron mobility transistors. So they also benefit from having a high stress for reasons which I cannot tell you because I don't know exactly. But there are these wafers commercially available, basically.
All right, thanks.
Is there any other questions? Yes.
So having two membranes will help because you place one membrane on one mirror, like the input mirror. What about placing another membrane at the end mirror as well?
Yeah, I mean, this is a membrane at the end mirror. Let's say, I mean, the way it's drawn here. So, okay, this is of course just a one-dimensional standing wave, but one point to consider is the shape of the mode, kind of, and you have curved wave fronts at this end mirror. So then this is not ideal with regard to the flat membrane. Then this obscures your cavity mode. So therefore, people typically put these membranes at the waist of the mode. But you could add additional membranes, of course, close to the input mirror, I think. But then you might,
Yeah, just to add to that, if you just from the GR, the effect is suppressed on the end mirror too. It's this point I was making before about the symmetry broken by the directional.
Yeah, this of course
so you don't want to put the membrane on the end mirror.
No, of course. I mean, there's various reasons why you don't want to put it there. Yes.
Okay. There's lots of discussion. Any other questions? Okay, if not, thanks a lot for the great talk, and